Okay, another important contract that we have in this application, the LunarSwap, it's the shielded ERC20 token flow. So we have a flow for minting and we have a flow for burning a token, and it's shielded. So this is one of the applications that we have available within Midnight blockchain. So for the case of mint flow, we have a constructor that only the admin is going to be able to create it. So the one that constructs the contract is going to be the admin. Then we have a evolve nonce that it's a prerequisite to actually mint a token. And then we have the actual function that mints the token, which is mint shielded token. And at the end, we're going to have a shielded coin info. For the case of burning, we're gonna call a receive shielded, and then we're gonna send an immediate shielded function to a burn address that could represent a actual burning or an actual transfer. So let's see how this translates into code. So let's go back here to section 4, where we're gonna analyze some snippets of the smart contract code for actually running and declaring these functions, the minting and burning. First, let's see what are the ledger states that we have for this contract. We have counter of type counter, nonce, total supply, types. These are variables that normally you declare when you want to have some kind of tokens, right? Like total supply. Then we have some sealed ledger variables. Sealed means that that only the contract can implement those during the construction. So it only happens once. So we have domain, name, symbols, decimals. Okay, let's see what we have for the circuit itself, the minting. So we are declaring here a circuit called mint, where we are passing a probe called recipient of type either a Zswap coin public key or a contract address. Right now, we are able to pay to Zswap coin public keys, which represents a user. Contract to contract communication is not available yet, but nevertheless, in this contract circuit, we are already declaring this type that accepts both Zswap and contract address. So it is compatible in the future when the contract to contract communication it's available. Then we are passing prop as well amount of type uint64. So let's see. Here we are doing an assertion to make sure if is key or address the recipient. As I mentioned, contract to contract communication it's not available yet, so we want to make sure that this prop it's only Zswap coin public. If it's a contract address, this is gonna fail. Okay, what else? If we have that, we're gonna increment the counter by 1, and then we're gonna evolve the nonce. So every time that I mint something, I want to have a new nonce. And I update that variable. What happens next? I'm calling this function that it's coming from the standard library, that it actually mints a shielded token. I need to pass the domain, I need to pass the amount, the nonce, and the recipient. And once that happens, I'm just here auto-detecting token type of first mint, and I am updating the total supply. Since I have minted some tokens, I want to update this total supply. So let's see what are the key patterns in this circuit. The either Zswap coin public key contract address, this is a polymorphic recipient mint to a user, wallet, or another contract. For now, contract to contract is not available. Evolve nonce. Each mint gets a unique nonce, so coins can't be correlated. Mint shielded token. The Midnight's native Zswap primitive creates a real shielded coin. So this is important. We have been talking a lot during these sessions. What is the Zswap primitive? And by using this function here, what we are actually doing is creating a token in the Zswap world. Okay, now disclose amount and disclose recipient. These values must be disclosed to enter the Zswap system. So you can see here that we are passing recipient and we're passing amount. Since these are props are coming from the off-chain part, we need to disclose them and let the compiler know that we are okay to disclose those values, so the compiler can use them to update a public state. Excellent. And now we have the burn circuit. So let's see what we have inside this circuit. We are passing a coin that is of type shielded coin info and an amount of type joint 188. So the coin is the representation of that coin in the Zswap world. We have this type, shielded coin info. So we are making sure, so we use this assert to compare things. The coin, which is of type shielded coin info, it has some other properties inside. One of that is color, the other one is value. Value, it's the value of that coin, and color, it's the type. Different coins, they have different colors. So in this case, I want that the color being passed to that circuit to have the same color as the type declared. Otherwise, it fails with this shielded token not created from this contract. And also, I want to make sure that the amount of tokens being passed to the circuit it's greater than this amount specified. Otherwise, it fails with insufficient token amount to burn. Okay, then I use this other function from the standard library as well that it receives those tokens. So it receives the coin into the contract. And then I update again the total supply. After that, I'm sending that shielded token to somebody. Once I'm using this send immediate because within the same circuit, I'm receiving the shielded token and I'm sending. So that's why I need to use this send immediate shielded. There's options where I'm not gonna need to use this immediate. I'm just gonna use send shielded. But in this case, we're using send immediate shielded. And we are passing the coin using this clause because coin it's part of the props being passed to that circuit. And then passing the shielded burn address and the amount. So in this case, the contract compiler and the language, it gives us this function here, which is a burn address that guarantees that whenever you send something to that address, it's never gonna be able to be retrieved. So it's burned. And then we have this if. In compact, we can have some logics using this primitive, like in TypeScript. So if this change, so send res, it's the result after sending some shielded. When I send token to someone, this works as UTXO. So it's not that I'm just sending the difference. I send everything that I have, and then I have some change. So I have a return. So in this case, that's embedded into this object. So by using this object, I have this other property called change is sum. So it means I have received any change. If this is true, then what I'm gonna do, I'm gonna declare this constant color to be a left of Zswap coin public key having the on public key. So what is this? Here we have defined that a person interacting with this could be a Zswap coin public key or a contract address of type could be maybe, could be both, could have only one, but we are using both cases because we want our contracts to be upgradable once we have contract to contract communication. So if I want to declare just only one, in this case, declare a value, I'm using the Zswap coin public key and passing the value here. On public key, it's a function, again, available within the standard library that grabs the coin public key from the person executing the circuit. And left, I'm saying that this on public key it's of type Zswap coin public key. Okay, then I'm sending the immediate shielded again to this caller. So I'm sending the change to the caller using this object send res that I got after sending immediate shielded up here. So you see the pattern here. I'm just making sure that some conditions are met using the coin color and coin value, and then I'm receiving the coin. I'm updating a constant, and if that constant after I'm sending the token, and if that change, if I actually have some change, then I'm executing this. I'm sending the change to somebody else. So that's the circuit, and that's how we interact with shielded coins in Midnight. Another feature that this application is providing us, which is really nice, it's the math library. We're gonna need that a lot using Compact, and we're gonna now understand how the off-chain and on-chain can work actually together. So let's understand this pattern. Off-chain compute, on-chain verify. So here it says Compact has no native large integer support, no variable bound loops. No, you can't just write A divided by B for a 128-bit division. So the witness pattern for math. You compute the answer off-chain, you pass the answer into the circuit, and then you verify that the answer is correct on-chain. So that's the pattern that you can do when you don't have the computation available on-chain only. So for example, here it's the implementation of a division, and it's being provided as a module within the OpenZeppelin library. Why this works? Division is expensive in a circuit, many constraints. Multiplication is cheap, one constraint. So you compute the hard part of chain using this witness division and verify the easy direction on chain. The proof guarantees the witness didn't cheat. So we have different libraries for that have been provided. For example, different purposes, division, limb-based, nested, limbs, byte level conversions, BLS 1238 scalar field arithmetic, generic packing, unpacking. You can see here the implementation of the square root. So we can use that as a module now. So let's see in a graph how all this works. So this is the pattern I was talking to you about. We have this off-chain, and then we have the on-chain, which is a circuit. A off-chain witness, it's normal TypeScript. So you have no constraint. You can do whatever it's allowed in TypeScript off-chain. So for example, we were defining these different Oracle functions that does some kind of computation available in TypeScript. And then we just send the proof. And on-chain in the circuit, we do the verification, which is cheap. For example, we assert that the multiplication of AB plus R is equal to A. We can assert that something is greater than something. We can simply check one constraint. So division, it's expensive in ZK, many constraints. So we do the opposite. We calculate that and we verify on-chain. So we now have all these libraries available, and this is something nice to have to perform some math that it's not available only on-chain. Okay, excellent. So with that, we have pretty much understand all the architecture of LunarSwap. What are the main circuits, how the contract is declared, how we create shielded tokens. So now we need to put that into a front end. So in this case, we're gonna need to connect to a wallet. We're gonna be using Lace, and this is how the connection flow happens. We check window midnight mn Lace if it exists. What happened? All these wallets, they're gonna have an extension, and you're gonna be able to connect to that wallet using the window object of each browser. Then you're gonna enable that connector. You're gonna connect, and you're gonna be able to have the state of the wallet, and then get some properties of that connection API. For example, service you reconfig or auto reconnect in case you have saved the state in local storage. Also, the wallet context patterns, you have wallet context, network context, and some utils. The nice part about this is that, for example, in the starter template of Edda Labs, we have provided you with a wallet widget. So you don't have to worry about the structure of this. You just grab the code from the wallet widget, and all this is integrated under the hood. The address types, we have the coin public key for receiving shielded coins and the encryption coin public key for encrypted communications. And the data flow at the end, the whole application would look like this. So the user clicks swap. React components called the contract API. This API grabs all the logic that we discussed during this session, plus the glue using Midnight.js. We build the circuit inputs, the lace wallet signs, and provides the proof server URL, and the proof server generates the CK proof. Once we have that, the wallet balances a transaction. It's going to add the transaction fees, in this case dust, and it's going to broadcast to the Midnight preprod. And the indexer is going to pick it up when it's processed by the node, and the UI it's going to re-render again with the updated information. So it's pretty much the same pattern as the bulletin board app. As I mentioned before, once we learn how all the systems connect each other in Midnight, what it's more important now is to understand the architecture of the actual smart contracts, because then the Midnight.js parts and integration with the UI, they are pretty much similar. Okay, perfect. So that's it for this session. As a takeaway, we're gonna see 3 things that it's worth remembering. OpenZeppelin patterns plus composable building blocks. Access control is imported by shielded ERC20, which is imported by LunarSwap. Same module system, CK native implementation. The witness pattern, it's the mental model for CK development. Compute off-chain, verify on-chain. You'll see it in the math, in the role management, in token operations, everywhere. Then another thing important to remember, it's Merkle trees plus nullifiers equal privacy preserving state management. So this is how you do access control, membership proof, and deduplication without revealing who or what. So what's next? This code, it's open source under this link. You can fork it, read the contracts, and build on top. And we have built some additional content based on this repo. You're gonna be able to see the explainer 8, where we did a quick version of why OpenZeppelin on Midnight matters, and a deep dive as well for a detailed breakdown of the CK access control patterns.